welcome back, everybody, and welcome to the second last week of the semester. So we quickly approaching the end of the academic fall semester, and last week is actually our last teaching week. And thereafter, I mean, it's the exam period, and then we have the winter break. So what we are going to do today is to try to finish the discussion we had on support vector machines, which is a very popular method. It is essentially a linear algebra and optimization problem. And we are going to mainly focus on classification. And then tomorrow, we are going to look at also how we can use these methods for regression. That means to fit a function. Now, before we move on with the topic which we started with last Friday, I wanted to say something about the eventual workshop which we could have tomorrow. And I would need an input from you people. But let me just quickly show you what we had, for instance, last year. So this was in 2020 during COVID, and then we had something like 8 presentations of the possible projects for project number 3. And you can see there's quite some scatter in the possible topics. So there was one person who actually looked at financial machine learning. So that person had actually data from the stock market in Sao Paulo in Brazil and wanted to simulate that with recurrent neural networks. So that's a possible project. And then in many of these cases, there's a lot of data which has actually been studied in the scientific literature, which means, again, that you can easily compare the methods you've been looking at with what has been published. And perhaps you can actually improve what has been done by other people. This is just an example of what we had in 2020 during COVID. Last year, still in some kind of COVID situation, but we had that the lectures were run in a hybrid mode. Then still many people were a little bit hesitant to stick their neck out of home. So we had only 4 people who actually presented different possible projects, and you can see the topics here. So if you wish to present something for project number 3, feel free to make a small presentation. It doesn't need to be very pretentious. I mean, people typically had a presentation of 5 to 10 minutes where they show the data they want to study and why they want to study this kind of data, and so on and so on. So it's not something which is meant to be streamlined and highly polished, but it's more the ideas. And what often happens is that other people think this is an interesting case, and they may even ask you if they can join your research group. So please to send me an email by the end of the day. If I don't hear anything, you will have to suffer me lecturing the whole day tomorrow, okay? So that's the penalty you have to pay if we don't have a workshop. You will have to listen to me. I don't know which you prefer. That's up to you guys. Now, anyway, these were just examples of what we've been having. Now, one of the things I wanted to say a little bit about is also the last project. I know that everybody is pretty stressed with the second project, and maybe your thoughts are elsewhere, but I just wanted to say something about the last project. And as you can see, the last project is actually something where you can actually define the data set. There is an interesting data set, actually, if you want to look at a problem which deals with finance. The only problem is that I think the data are a little bit difficult to get access to, but there's actually data on bankruptcy studies in Spain. So they have data on companies which file bankruptcy after some time. And then they try to find indicators which could actually tell the banks whether this company could fail or not. And this is obviously something which insurance companies and banks want to have a kind of handle on. I mean, what is the likelihood that a specific customer or somebody who takes up a loan can actually go bankruptcy? In connection with that, I like to mention if you guys, if somebody is looking after a master thesis topic where you want to apply machine learning to financial problems, we do have a former computational science student who works with a financial company, and they have the bankruptcy data for Norway. Now, many of these data are not accessible, but that's a project, and they're actually also interested in people who could analyze this data as a kind of summer job or just as an internship job. So if you're interested, just shoot me an email and I can put you in contact with Sebastian is his name actually. You can also, if you look at the kind of methods we have covered. So one thing which we had last year, it was a whole group who studied decision trees, bagging and boosting methods, and studied things like the bias variance trade-off. They looked at both regression cases. They wrote their own bagging code. They wrote their own boosting code, and then compare that with, for instance, extreme gradient boosting, this highly streamlined library for high performance computing. So this is also one possibility, that you take, let's say, a set of methods, and decision trees and ensembles of trees is something which lends itself easily to such a topic. And then you could simply study these methods. You could develop the software which is needed, and then run an analysis of specific data sets. So you can actually pick data sets or methods which you find interesting. We had another group some years ago who actually looked at gradient optimization methods. And they were interested in exploring these methods on different types of data sets. And then in conjunction with, let's say, neural networks, like you've been doing now in project number 2, but spend more time on studies of different optimization and gradient descent methods. So this is, again, another possibility. But you should feel free in a way to come up with your own suggestions. And if not, there is one path which we normally have called the kind of standard path, where we actually suggest something. And this is actually a topic on solving differential equations and partial differential equations with deep learning methods. This is a pretty hot topic if you are dealing with partial differential equations in your research. Especially if you're looking at high dimensional problems, because then what often happens, if you're looking at, let's say, the 3-dimensional solution of the Navier-Stokes equations, and you want to study something like turbulence, that means you need to have a very fine grid, the resolution, when your computational resolution. And that can be beyond what is the feasibility of present codes. And that's a field where machine learning has been applied in a way as a way to reduce the dimensionality of the problem. So if you're interested in this topic, I know that we've always had a group of people who follow a course which is called IN 5720, which is called Numerical Partial Differential Equations. And this course actually, this project fits well if you have solved, for instance, the wave equation in 1 or 2 dimensions. So that's one possibility, and we're actually going to look at the in this case, the heat equation for standard diffusion, which you see here. And we're going to limit ourselves to a 1-dimensional problem. And so here you would set up the problem, and then there is just a standard solver where you can use a forward method like Euler's algorithm for solving the differential equations, and then you would compare that with neural networks. Typically, the project should follow the same lines as you've done before. So you need to structure the data very much in the same way as you did in projects 1 and 2. You should explain how the data are produced and place them in a proper context. So if you pick a data set, let's say like the Wisconsin breast cancer data set, you should obviously describe the data set, even if you had it in project number 2. So it's important to actually describe and tell the reader about the data set. Because if you choose your own data set, an important part of the project then is actually to explain the data set. Because else, when we read them, we would clearly have problems in understanding where do the data come from, how was it scaled, and et cetera, et cetera. So the way you prepare the data set, and where it comes from, how things were extracted, if there were problems with the data set, these are also things which are essential to discuss. So there is a famous data set on credit card defaults, so people not paying their credit card debt. And if you go into the data set, what you will typically see is that lots of the data are punched in wrongly, because there's a human who was supposed to punch 1 or 0 when you pay your credit card debt or not. And then you can punch 2 instead of 1 and 0. And so you can see typically in the data set there are clear errors. So preparing the data set, discussing it, is something which becomes then important for the report. Then, if you proceed, then you need to discuss at least 2 of the central algorithms which we have in the course here. So that's something which you should actually apply at least 2 of the algorithms we have discussed. And so this could easily be the algorithms of your choice. Then you describe your algorithm and implementation as you've done before. Present your results and findings, and link with existing literature if there is a possibility like that. And many of the data sets which you find up here, if you go up to the top of it, you will find the data set Kaggle. I guess everybody has seen that data set. They often, companies that would actually publish competitions there, who is actually able to reproduce the data set in the best possible way. If some of you is more into particle physics, there is a famous challenge from CERN on classifying the Higgs events from 2014. And that's a challenge which is out there online. Just search for the Higgs challenge. And then you could apply the methods which we have been discussing here. I mean, decision trees, random forests, neural networks, et cetera, et cetera. There's also the University of California and at Irvine, which actually has a machine learning repository, which I normally recommend. And there are tons of data sets. There are tens of thousands of different data sets. So feel free to search a little bit, but also don't wait with sending me an input about whether you would like to present to everybody else a possible project. And we're going to do that tomorrow. Any questions about the last project? Things which are unclear? So how many of you are thinking of doing your own data set? Or are you still, at least one? I guess everybody's still within the context of project number 2. Right? Okay, so what I wanted to do next now is to say a little bit about what we did last week about support vector machines. And if you don't have any questions, I just wanted to move on a little bit and say a little bit about support vector machines. And support vector machines is a method which was introduced in the 90s, in the previous millennium. It's always great when you can say millennium instead of a century. It feels like ages ago, right? And the method is a method where the basic idea is actually to be able to separate different classes. So it was first tailored to classification problems. And tomorrow we are going to look at also how you can do that for regression types of problems. And what you typically hope is that the domains of events and classes you want to classify can be well separated from the beginning. And then you want to find a way to predict the different classes without storing too much data about the model which you make and which you fit to the data. So one of the things which we discussed last time is this introduction of a margin, where we actually separate the 2 classes by looking at the points which are closest to a midpoint or a plane which separates the 2 faces or the 2 classes. And then if we have more classes, we actually end up with a hyperplane. If we have 3 classes, it will typically be a plane, because then we have a 3-dimensional problem. If we have only two classes, it's typically just a line which separates the two classes, etc., etc. So the way we define this separation area is the topic of support vector machines. And what it leads to is a optimization problem where you introduce a Lagrangian. So I'm going today to remind you a little bit about Lagrangian calculus, because that's a very useful way when you are solving an optimization problem with a constraint. So typically till now, the optimization problem we have solved is us computing the gradients and putting them to 0. So that means that all the points which are defined within the domain we have to define the data set, they will be included in the optimization. But if you have an optimization problem with a constraint, you're just looking for some particular solution. So if you have a line which intersects the function you want to optimize, then you're looking after the points where this line intersects the function. And that would be the solution to your problem. So we are now going to look at an optimization problem with a constraint. And last week, we defined this constraint to be the margin between the data set or the classes which we have. So let me quickly remind you of the basic mathematics by just spooling back to this problem in 2 dimensions, and where we could simply just draw a line between the different classes, okay? So let me bring up the whiteboard here. But before we do that, let me just show you one of the examples which we have in the, which we also went through last time. And now I need to find back my other browser where I have my Jupyter notebook. Here we are. So one of the examples which we looked at last time and that's a typical example of a class where we can separate the 2 classes very easily. So if we now look at what is plotted here, this is the petal length against the petal width of 2 classes of plants. And you see now that the data points are pretty well separated in this specific case. So that means that in this case, we could actually fit a line which just separates the 2 classes. And then you could say, if you're above the line, you belong to class 1. If you're below the line, you belong to class 2. So this is a very simple way of illustrating what we are looking at. And in many cases, we do actually have well-separated classes. But then, as we will see today, one of the problems we will face is a case where we have 2 classes which are not well separated. And then there are different ways by which we can transform the problem so that we again get 2 classes which are well separated. But in this case here, this linear SCV is actually a support vector machine which uses a kernel, which is linear. And then there's just a simple support vector machine, the SVC, and I'm going to describe to you what this actually means. And then there is just a simple classifier where we try to just fit a line through the areas here. And then the thing you see now with the simple classifier is that this line can take different slopes. So there are tons of lines which actually make the prediction for you. Now, with the support vector machines, you want to identify very clearly the domain which separates the 2 classes. So let me just bring back the notebook then, and just keep this example in mind. And then we are going to look at the basic mathematics which we introduced last time, and try to link that with that figure which you saw now. So let's bring back the notebook. So what we did last time was to define the regions which we want to have as a way to define a model which separates the 2 classes. So let's just bring this back. So we have support vector machines. And this is often when you're dealing with a classification problem, it's often written as an SVC, support vector machine for classification. And the example which we looked at last time was an example like this with two features, x1 and x2 here. And then we had some observations. And I'm just going to mark the observations like this. And then we had the circles. So this was an example of well-separated classes. And we call this class C1. And this was class C2. And we had only two types of outputs. So we had an output y of I, which could be either -1, which in our case corresponded to class 2. This is the way we classify these data sets, or +1. So +1 is a case which we then refer to as class 1. So this would correspond to y of I equal to +1. And this would correspond to y of I equal to -1. And for this specific case, what we could do, we could actually use standard linear regression and just find a line. Now, the problem there is that depending on the slope, we could have many different lines. So what we want to have is a well-defined region, which allows us to say that outside this region, we are either in class 2 or in class 1. So you could have in the plane here, what you would have then would typically be something like a line which separates the two classes. And then the topic which we defined is something which we call the margin. And the margin was defined as the shortest distance. So we define this as a margin, which is, if you now think of these as vectors, which is orthogonal to the line which divides the two classes. So on this line, which you see here, what we have done then is to define a function y tilde of I, which is given by this fx of I, which is exactly equal to 0. So there we predict 0. So what you could say now, if you find such a line where your prediction is equal to 0, then you would say that if a point is above, so if f of x is larger than 0, you are in class 1. If f of x is less than 0, you're in class 2. That sound obvious? So the point here with the support vector machines is that this margin is now going to be defined by the points which are closest to this separation line. And when you make a model now, you're going only to keep the data for those points which are on the margin. So that means that this is these vectors, which then are labeled support vectors, are the data which you keep as your model prediction. So in the training here, what we are looking after is actually a line like this, which separates the two classes. If you are in 3 dimensions, this is going to be a plane. And that means that this margin will be defined by a vector which is orthogonal to the plane. Now it's a vector which is orthogonal to the line which separates the two classes, what we might call the midpoint line. So what you're going to do then, when we are setting up the model here, is that we are going to have, when we now have y of I multiplied with this f of x of I, we obviously want this one to be larger than 0. This is the ideal. And that's because if we predict +1 and the output is +1, this is larger than 0. If we predict -1 and then the output is -1, then we also get +1. So this is the way we are going to gauge whether we have a correct prediction. If it's less than 0, then we are predicting wrongly because we have only two outputs, -1 and +1. So if the model which we have made doesn't make the correct prediction, then we are wrong. So this model which we made then is a model which we put up in terms of, for the 2-dimensional case which we are looking at now. This is going to be given by a vector W, which is the unknown quantity, which we want to optimize, multiplied with a vector x. So this looks like us fitting a line here, plus a term W0, which we could think of as a bias, or in case of fitting a line, we could think of that as the intercept. So this is the kind of model which we want to make. And let me remind you a little bit of the mathematics, or rather the geometry, which we looked at last time, because then we need to bring up some of the quantities which we defined. So this is the model which we want to make. And this W in this specific case, since we only have x1 and x2, is going to be given by W1 times x1 plus a W2 times x2 plus a W0. And when we are on the line which separates the two classes, so when we are on that line, then we have f of x of I equal to 0. So that defines a point on the line. So a point on the midpoint line or just call this the midpoint line. Let's call this x of A. That has a value which has to be equal to 0. So any point on that line, we make a prediction f of x equal to 0. Okay, let's bring back some geometry here, and let's make a graph where we now set up the midpoint line. So we have this line here. So we have defined an origin. So this problem is always related to an origin which you define. So what it means now is that we would have these vectors, because if you now look at the case when we have a point on the midpoint line, this means simply that our vector W has to be a vector which is orthogonal to the midpoint line, as we discussed last week. So this would be the vector W. And this vector is not necessarily a vector which hits the midpoint line immediately, but we could actually draw it more like this. So we could have a vector which points in this direction, and then we can elongate it by multiplying with a factor. So this is the vector W, and then we have a vector which now defines a point up here. Let's call this point X. And this could be now rewritten in terms of X of X with a line perpendicular or on the line here. And we know that this Y tilde of X perpendicular is the same as our function X perpendicular, and that's equal to 0 because that's on the line. This is a definition which we put up. And then we could now add a piece here, delta. And this delta is actually a quantity which we have used now to scale if we now continue W. So this delta is now going to be, this last piece here is going to be given by delta. And then we have the vector W. So delta is just a constant. And this is divided by a norm of this vector here. So what we have now is just a constant, which now brings us to the final point, where we have one vector, x perpendicular, plus the other vector delta, which then finally brings us to the point x, which you have here. Okay? Does that sound okay? So it shouldn't be too difficult. So what we did last time, and let me remind you of that. So we have now x, which is given by this x, the perpendicular piece, and then we have plus this vector W, which is perpendicular to the line, and divided with its norm. So we have actually scaled this quantity, and we're just multiplying with a constant, so we reach the right point. And then we know that our function y tilde of this x is equal to 0. and that is given by WT times X, W transpose, multiplied with this vector plus W0. And then what we did last time was actually to find that this delta, so this is basically where we ended last week, this is given by Y tilde of X divided by this norm here of 2 here. And the thing which we wanted to do now is actually to define a kind of margin. And what we ended up with then is to require, so obviously what we are interested in is the case now where when we now take our quantity here and multiply Y of I, which is the output, and then we have fitted a function Y tilde multiplied with X of I plus W0 divided, so this is the model which we are dealing with, divided with a norm. Now, instead of having this larger than 0, we actually want this to be larger or equal to this point M. So we could put this to 0, that means that we just have a line. But now what we are saying is that we want to define a region, this kind of barren land here. So we would have this region which you see here. And this is now a region which separates clearly the 2 classes. And then we define this margin M to be the largest possible value which separates the 2 classes. Does that sound obvious? Because if we make the smallest one, then we will be back on the line. So we now want the largest possible margin which separates the 2 classes so that we hit the first points which are on the margin, which then define the distance between the margin and the midpoint line. So the kind of problem we want to solve is a problem of this type here, which again, when we now look at it, means that we are going to have Y of I. This is our data. So we take, this is data is -1 or +1. We have the function, which we call Y of I tilde, which is now Y of I multiplied. And now we're going to multiply away this W. And this is essentially what we have here. So we took Wi X of I plus W0. And we want this one to be larger than M and divided, multiplied with this vector, the norm of this vector here. So that's the quantity we want to find. And we want to find this for all I from 0, 1, and up to n-1 here. And what we have here actually, when you also look at the function f, which we put in here, so f divided by this quantity here is nothing but this quantity which you see here, this delta. And that's often called the signed difference. Okay, so what we are going to do now, and I'm going to show you later that this is actually correct. So we can now maximize this quantity M subject to the constraint that this quantity now, and what we're going to do is actually to say that M, because M is just a constant, and W is a normalization factor, which we can choose to normalize to 1 if we want to, but we can set this quantity equal to 1, because keep in mind now that M is just a constant. So M scaled with this norm of the vector, we just want this one to be equal to 1. So that means that what we could do now, if this is the case, so that means that M is simply given by 1 divided by the norm here. So we want to maximize this quantity M with respect to W and W0 with a constraint And since we now put this to 1, then what we have is y times wt of x of I plus this w0. And we want this one to be larger or equal than 1. Okay? So just keep in mind that m multiplied with this norm is something which we can always define to be equal to 1, because these are just numbers. So when we normalize the vector and we construct this quantity delta, which you see here, so we can always normalize things when we construct this vector so that the product of this norm multiplied with m is equal to 1. Now, when we now have the maximization of m, what we can do then is to convert that one to a minimization problem. If you look at the definition of m, the way we put it up here, m here, so m is a we are going to maximize it. And as I said, if you minimize it, then you would just be on the line. And this is something you don't want. Then maximizing this is the same as minimizing this quantity here, right? Does that sound reasonable? Any questions so far? So alternatively, what we can do then, or minimize, and we are going to add, for the sake of convenience, we're going to add a factor of 1/2, because then when we're going to take the derivatives now, we are going to get rid of the factor of 1/2. So when we look at the norm, this is actually the same as the transpose of W, so just the inner product, multiplied with W, under the constraint of W. So we're minimizing with respect to these parameters, with a constraint of y of I multiplied with Wt of x of I plus W0 larger or equal than 1. So this is the basic problem which we now want to solve. So how do you actually, what kind of problem is this? So if you spool back to mathematics courses, you may have seen this before, but normally it's not the kind of main focus of, let's say, the standard linear algebra courses, but you may have encountered it. Anyone who remembers what you typically call that problem? It's an optimization problem with a constraint. And that leads to the theory of Lagrangians and Lagrangian multipliers. Does that ring a bell back from your mathematics courses? When somebody did perhaps an optimization problem where you had additional parameters because not all the variables are now independent. So that leads to the theory of Lagrangian multipliers and Lagrangian optimization. So since I see that not everybody is familiar with it, let me try to bring this up. So I'm going to spend a little bit of time on the theory of optimization with the Lagrangians. So that means simply an optimization problem with a constraint. Because keep in mind now that what we have done till now is actually us calculating the gradient and putting that to 0. That's essentially what you did in project 1. And you've partly been doing that in project 2, except with the back propagation, you don't want to drive the gradients in each layer to 0, because then the training stops. But essentially what you want to is to have the gradient of your cost function to be 0. Okay, so what we have here is normally called an optimization problem with a constraint. So this is an optimization problem with constraint. So let me show you this with an example. So let's do that. This is actually just another way of optimizing your problem. So what we would like to is to find extreme values of a function which I'm going to just call f of x1 and x2 And this function is given by x1 squared minus x2 squared when x1 is larger or equal to 0 and x2 is larger or equal to 0. This is a typical optimization problem with a constraint. So that means that we're actually going to limit ourselves to the quadrant where x1 is larger than 0, equal to 0, and x2 is larger equal to 0. So that's a typical case where we deal with that. So if you now think of the general type of problem, what you could think of now is that you have a function f of x. This is a general case. And you have an f of x. We assume that this is a real function and it has n entries. And this has constraints. And constraints of the type where we actually have functions, where we now have something like a g1 of x, and x can be a vector. Keep that in mind. So I'm not specifying whether x is a scalar or a vector. We could have a gx, g1 equal to b1. We could have a new constraint equal b2. So we could have a series of constraints up to gn of x equal to some value b of n. That's another type of problem. And the way you solve this type of problem where the b of i's are constants, to find the extremes, you would then introduce what's called the Lagrangian. Introduce the Lagrangian. And this is now given as a function with x and a function of lambda, where lambda now can take several values. So we have an f of x. So remember now that x can be a vector, it can be a scalar. And I have different values of lambda. So I have a lambda 1, where I now have this g1 of x minus b1 minus, and this goes all the way up to a lambda of m. And then I have this function gm of x minus b of n. So what happens when you have constraints? So every constraint imposes a condition of dependence between the variables. So think of now you having a function which depends on x1 and x2. If I have one constraint which constrains x1 and x2, it means that only one of them will be independent. The other one will be related to the other one via the constraint. Okay? So this is basically the formalism which is used when you have constraints, and it's called the theory of the Lagrangians with Lagrangian multipliers. And you've probably seen something like that in some of the early mathematics courses. But it depends again on what kind of problems the different teachers emphasize. But I assume that, I think you've seen it, but it takes some time to spool back the memory or reboot the memory here. So if you now look at an example, what you would typically do now is that these parameters, lambda 1, lambda 2, lambda m, they are called Lagrangian multipliers. Lagrangian or Lagrange multipliers. And the recipe now, in order to find the solution to the problem, is that what you would do is to, in this case, to have a calculate the partial derivatives with respect to the different values x. So if x is more than one dimension, you would have x1, x2, x3, and so on. And you're going to put these to 0 for I from 0 up to n minus 1. And then you would have similar equations for these parameters, where you now have a d of lambda j equal to 0. And that's going to be for j equal 1, 2, up to this parameter n, depending on the number of constraints which you have. So after the break, we are going to show how you can employ this with a new example. So this is a simple case where we define f of x1, x2 equal to x1 plus 3 times x2, and this is subject to a constraint, x1 squared plus x2 squared equal to 10. So what that means is that we are making a circle with radius 10, and we are going to search for the solution on the surface of that circle. It's actually on the perimeter of the circle. So we are then going to plot x1 and x2 against each other. That is a straight line, right? And where that line intersects the circle, x squared plus y squared, that's where we will have the solution to the problem. And then we are going to use this formalism with the Lagrangian multipliers and Lagrangians to find these values with a constraint. So as I said, now we are moving away from what we have done before, where we simply calculate the gradient and we put the gradient to 0. And then we would search for the solution within the whole domain of variables, which define the specific function. Now we are going to find the solution on the boundary, defined by the constraint. So that's the basic difference. So just think of the first one. This is just a straight line in x1 and x2. And where that line intersects the circle with radius 10, that's where we have the solution. And since this is a straight line, which goes from minus infinity to plus infinity, you shouldn't be surprised that there will be two solutions, right? That's where a line intersects a circle, right? And we are going to see that after in the break. And then we are going to go back to the problem with the margin and support vector machines and use this technique of Lagrangians in order to find the optimal parameters with a given constraint. And that's the basic recipe. If you have this present, then you have the basic recipe of support vector machines. So it's actually, the idea itself is very ingenious and very simple. Okay, I went a little bit over time because I just wanted to finish this point. So let's be back at 20 past the hour. Is that okay with everybody? I just stole 5 minutes of your life. I'm actually stealing a lot of time, even more with the projects. So I owe you a lot of time back here. Huh? Okay, guys, let's take a small break. And feel free to ask. Okay, so the problem you see now is a problem which, in this case, shouldn't be too difficult. We could actually almost solve it without including anything about Lagrangians, but I'm taking the liberty of using this simpler problem so that we can illustrate the principles. So if you now look at the function which we are meant to plot here, so if we make a plot, and you already know now that my plots are not the best ones. I should have made a plot in the lecture notes with a Python code. So you would have a 1, 2, and this goes all the way out to 10. And actually it's a square root. We go out to, this would be the square root of 10, somewhere in here. And then we would have the same here, minus 1, minus 2, minus 1, minus 2, etc. And then 1, 2, this should be the square root of 10 somewhere, etc. So you could now think of a circle which now represents the boundary or the constraint which we have. And you can see that my kind of drawings are not the best ones. So this should be x1 squared plus x2 squared equal to 10. That's a constraint which we are putting in. And then we are going to draw a line, which then crosses this circle somewhere. So when x1 is 1, x2 is has a value, and if x1 is 1 and x2 is equal to 1, then we have 3 times x2. So that should be up somewhere here. So let's just draw a line like this. And these are the points which we are looking after for x1 and x2 here. Okay? So now we're going to use this kind of Lagrangian formalism to find these values. And the first thing which we end up doing now is to set up the derivatives. So we're going to take the derivative of this Lagrangian, which is dx1. and this is going to be the derivative with respect to x1 of the function where we have x1 plus 3 times x2 minus, and then we have this Lagrangian parameter lambda, and this is given by x1 squared plus x2 squared minus 10. So this is the function we want to take the derivative of. So what you see here, this defines our Lagrangian in terms of the function f of x, where x now is a vector containing x1 and x2 minus lambda times a function g of x, where this g of x is x1 squared plus x2 squared minus 10. And if I take the derivative now, and I require that this one is equal to 0, this gives us 1 minus 2 lambda x1 equal to 0. So we get then that x1 is equal to a half times lambda. And then I can repeat the same for x2. Want that to be 0. And that means simply then that x2 is going to be equal to 3 divided by 2 times lambda. So that will be the case for x2. And then we repeat for lambda. So we take the derivative of this Lagrangian with respect to this only parameter because we have only one constraint, and we want that to be 0. And this is simply x1 squared plus x2 squared. And this is now going to simply to be equal to 10. Because we get x1 squared plus x2 squared minus 10 equal to 0. And that means simply that we get x1 squared plus x2 squared equal to 10. And then we can plug in x1 and x2. So if I put in these two values in here, and I put that one in here, then I get a simple equation, which goes like 4 lambda squared plus 9 divided by 4 lambda squared equal to 10. Multiply out with 4 lambda squared, and then you find easily the final result, which then is simply lambda is equal to plus minus a half. And if I plug that in, I have two solutions. I get lambda equal to plus 1/2, and that gives us x1 equal to 1, and and x2 equal to 3. And then I have lambda equal to minus a half, and that gives me x1 equal to minus 1, and x2 equal to minus 3. And you can quickly see that if you plug in the values, that satisfies the constraint which we have. So we have now two solutions. So we have an optimization problem of a given function with a constraint. And that means that we are now no longer looking at all the possible values of x1 and x2, where we minimize the function f of x, but we're actually looking at the optimal values, which are defined by the constraint. And that means that we are now trying to find a solution on the perimeter of this circle. That sound okay? Hope people don't get offended if it's too simple. You can obviously look at more equations, but let's bring in an element which is called the KKT conditions, which we need to deal with when we are now setting up this kind of optimization problems. So these are called K, after a guy called Kusher, and Kuhn, and T for Tucker conditions. And let's look at a typical problem which we're going to encounter. So the kind of solutions which we have now, when we constrain the solutions, so we could have a lambda which is, or g of x, which is larger than 0. So when we look at these constrained solutions, let's take a closer look at it, because there are some specific conditions which we are going to use. So a typical solution which we have is this function g of x, which we mentioned, which now contains the constraint, which is larger than 0. So in principle, that means that the constraint is inactive. If you go back to the simple example we have here, if I took this function g of x, which is x1 plus x2 minus 10, larger than 0, that means essentially I could have all kinds of values for x1 and x2. So what I would typically say then is that this g of x, that is a case where the constraint is inactive. And then if it is not, if I have g of x equal to 0, then we say obviously that the constraint is active, because then we have an explicit constraint. And let's look at an example here. So we could have a function now, f of x1 and x2, which is given by circles, depending on the values of x1 and x2 here. So this is the function which we have. And then if we project this one into the x1, x2 plane, this is just going to be given by, so think of now having this as a function which depends on x1 and x2, and then we project that one into the plane. This is going to look like something like this. So we will have different circles depending on the values of x1 and x2 squared, and we look at the projection of a given surface down to the plane. Okay? Then what we could have now is a constraint where we say that the g of x1, x2 is equal to x1 plus x2 minus 1. So that means that somewhere here, if we now look at the surface here, we hit one of these surfaces here. We hit several of them actually. But then we have an optimal value here of x1 and x2. So I'm just going to write this as an x star here. So these would be the optimal values. And if I now put, when this function g of x is larger than 0, then it plays no role in the optimization. Then it plays no role. In the optimization. And the minimum or the stationary points are then given, and the stationary points they are then given by simply taking the derivatives of the function f of x, are given by the gradient of f of x with respect to x here equal to 0. And this has a Lagrangian multiplier, which we put equal to 0. When the solution is on the boundary, so when the solution is on the boundary, so let's just put that up here. That means we have the constraint is on the boundary. Then what we have is that g of x is equal to 0. And in that case, we would have this function lambda, or no, this variable lambda, different from 0. But in both cases, what we can do now, for either case, what we can set then is that we have lambda times g of x. This is a condition equal to 0. And if we maximize f of x subject to g of x large equal to 0, then this is going to give us this KKT conditions. So if we now maximize f of x subject to g of x larger or equal than 0, then this kind of solution is obtained. We optimize, we optimize this Lagrangian L with respect to WRT, x and lambda, subject to the following. Subject to, we have g of x larger or equal than 0, lambda larger or equal than 0, and we have the condition that g of x on the boundary is equal to 0. These conditions which you see here now, they are called the KKT conditions, or the Kusher-Kuhn-Tucker conditions. And if you look at this kind of simple geometrical model which we made up here, that should in a way illustrate the kind of constraints and conditions which we get when we now want to optimize this function, which is called the Lagrangian. So the solutions is on the boundary. That means that this g of x is equal to 0. And that means clearly that this lambda should be different from 0. And then for either case, we can put lambda times g of x equal to 0. And you're going to see these conditions popping up again when we now are going to spell out the equations for the support vector machine for classification problem. So if we want to minimize, so typically you distinguish between minimization and maximization. For minimization, these are conditions apply again, but the only difference is now that the Lagrangian is the difference between the function we want to optimize minus the constraint which we have there, lambda times, let me just write this better, of lambda times this g of x, with the same constraint as above, with same KKT conditions. And it's pretty easy to see that. So these conditions just follow from the type of problem which we are now trying to optimize. And we are going to use these conditions now in order to find the optimal way to define this margin. So let's go back to the problem which we had. And let's now look at our optimization problem. So the support vector machine with classification and what we normally call the margin with classification and a margin M. So what we have is an optimization problem where we want to minimize. And now I just add a factor of a half to the norm of this unknown quantity W. And we want to minimize that with respect to W and this W0, which you can treat as a bias if you think in terms of neural networks. Or if you're thinking in terms of a linear regression problem, you could think of that as your intercept, if you're thinking of a straight line. But that's where the parallel actually stops, because when you move on to higher dimensions, this is no longer an intercept. We minimize this quantity, and then we have subject to, and we have a subject to y of I multiplied with this WT of x of I plus of this W0. And we now want this to be equal to 1. This is actually what defines the margin. So if you're larger than 1, then we are actually going to classify correctly. But if we have it equal to 1, we are actually on the margin. If we put that one to 0, then we would be in 2 dimensions, we would be on the line which separates the two classes. We would be on this line, which we call the midpoint line. If you are in 3 dimensions, this will be a plane which separates the classes. But now we actually want to fulfill this condition here because we want to find those points which define the margin. And we are only going to take to save the points which define the margin. And that is going to be our model. Okay, so just to remind you, what we have in 2 dimensions is a problem of this type, which you see up here. So we now want to find what is the point or the points which are close, which are on this line, which now defines this margin M here. So the points which are closest to the midpoint line in this two-dimensional problem. And then we are only going to store the results which define these points. And these points define then, with respect to a given origo, which you have defined, they define the support vectors. So the points are just called the support vectors. And if it's only one or two, this means that you just store the information about these 2 points. So let's now look at the Lagrangian, which we're going to look at. So we are going to treat this as a minimization problem. So we're going to have WT minus, and now we have a sum which runs over all the data points. And each of these now is multiplied with a Lagrangian multiplier, because we have the number of constraints for all I from 0, 1, up to n minus 1. So we have a constraint on all the points which we have. This is where we want to find the Lagrangian multipliers for. And this is multiplied with the function g as we have defined it. And these are the data, wi. The only unknown quantities is w and w0, plus w0, and then it's minus 1 here. So this is the Lagrangian. This is the way we are actually going to encode and use the Lagrangian formalism, the way we encode this optimization problem with a constraint. And this falls within the field in mathematics, which is called convex optimization problems. And this is a huge field in mathematics. I actually love that topic, but it doesn't sound like the most exciting topic. But it's a very important topic, because this type of problem, these problems are actually problems which we encounter in many applications in science, not only in natural science, but in all sciences. So this kind of optimization problems with constraints is something which is pretty common. So here, what we will do next is obviously to use the Lagrangian formalism. So we are going to calculate the derivative of this Lagrangian function with respect to W0. We want to put that one to 0. This is pretty easy to calculate, right? Because this gives us simply minus y of I times lambda y, right? If you look at the function, this is actually what we're going to get as a derivative. No surprise there. Then the next thing we're going to do now is actually to calculate the derivative. And now I take the derivative with respect to WT transpose, and we want to put that one to 0. And now you see the reason why I have this factor of a half, because then when I take the derivative of W squared, I get a factor of 2, which cancels the factor of a half. So I get W0 minus, and then what I get next is simply a sum over I, and then I have a lambda of I, y of I, and x of I. So keep in mind now that x is a vector, x of I. So I'm just going to put an arrow here just to remind you that this is a vector. Because if you look at the equation which we had, this is a vector, and that means that xi has to be a vector. So what we are doing here is just the inner product of 2 vectors. But just keep that in mind, even if the notation looks very compact. Y of I takes only values minus 1 and plus 1 in the example which we have chosen here. And then the final one is actually to take the derivative with respect to this lambda of I here. And this is a pretty obvious one, because that simply tells us that we have y of I multiplied with wt x of I plus w0 minus 1. And that leads to the constraint which we had with this KKT conditions, which you see up here. So when we had the constraints here, this is actually one of the constraints which we looked at. So what we can do next now, if you look at the equations which we have now an expression for W. So W is given by I, the sum over I, of lambda of I, of y of I, of x of I. So what I'm going to do now is to put them back into the expression for the Lagrangian. And then we are going to set up the final optimization problem with its constraints. And then I'm going to show you tomorrow, I'm going to show you actually how you can solve this problem numerically. And with Python, you have a library which is called convex optimization. So you can actually load in that library, which is actually called CVX-opt. And with that library, you can actually solve this type of problems. So what I'm going to show you is how you can convert these problems in terms of matrices and vectors, which you can feed into the convex optimization library, which you can download and install on your laptops. But take now a look at the expression which we have here. If you look at this one, what I'm going to do now is simply to go back here and plug it in here and plug it in here. So that means I'm going to set it in here and here. And I'm going to simply rewrite this one. And when you now take the function here, this is obviously going to give us a sum, which is also multiplied with a factor of a half. And then when we plug it into the next equation, we have a minus factor 1. So that means that when we do the algebra here, so we insert this one, insert W in L. And then what we are going to get is the following. So are going to have a new value for L. I'm just going to give you the answer here, but you can easily convince yourself that it is correct, of n minus 1 of lambda of I. And this is given by minus 1/2. And now I have a double sum here of ij. I have a lambda of I, a lambda of j. I have y of I, y of j. And now I have the vectors x of I transpose of x of j. Because I'm simply plugging in this value for W, which is a sum, and I'm putting that back into the Lagrangian. So then, this is subject to the following, and these are the KKT conditions. Check 2, so this is the KKT. This is subject to lambda of I, larger or equal than 0. I have a sum over lambda I multiplied with y of I equal to 0. And what we have next is that lambda of I multiplied with y of I. This is the same as lambda times g of x in this derivation of the KKT conditions of WT of x of I plus W0 minus 1, like that. And if lambda of I is larger than 0, then what we have y of I times WT x of I plus W0 is equal to 1. And xi is then on the boundary. So xi is on the boundary. In our case, this defines the margin M. And these points which are on the boundary, that means that this condition is fulfilled. These points are called the support vectors. And these points define the support vectors. So remember now that these points are related to a given origin, and then the coupling between the origin and the point defines a vector. So these points are then called the support vectors, and these are the points we are looking after. And this is the problem we now want to solve. So if we just repeat a little bit, we have a Lagrangian, which contains this unknown parameter lambda I. We need to find that one. We have the Lagrangian, which we need to plug in a optimization problem. And this is subject to specific conditions now. And using a given optimization algorithm, we can actually find the unknown quantities lambda and the unknown quantities W and W0. So when we found these points, we would then go back and define the parameter W0 and the support vectors at the end. Now you can rewrite this Lagrangian in the following form. So let's look at the rewrite here. Oh, by the way, this is normally referred to, the problem which we have here is referred to as a hard margin problem. So it's a hard margin because what we are assuming here is that if we now go back to the drawing which we made in the previous lecture, what we have assumed is that these two classes are well separated. That we have a situation like this where we can define a clear margin which separates the two classes. Now, you could actually think of you having some kind of admixtures in this kind of a barren region, right? So you could think of having some circles here, you could have a cross here, you could even have a cross up here, you could have a circle here, and so on. So there are two ways to circumvent that. The simple brute force one is to introduce a slack parameter where you actually allow for some of the points to be misclassified. Another way, however, is actually to rotate your domain or transform your domain x1, x2 in this case, so that the two classes are separated again. And that leads to what is normally called a kernel approximation. And we will discuss that in more detail tomorrow. However, the matrix we're going to set up is going to be more or less the same, irrespective of type of method. So let me show you an example on the Jupyter notebook of a case where we have a domain where we cannot separate cleanly the different variables. And then we go back to the details. But before we do that, let me try to rewrite this problem in terms of a matrix vector problem. So if we now look back at the equations which we set up with the constraints, so this is the Lagrangian rewritten after we have found the expressions for the weights, or the W's, which we haven't defined. But now we need to solve this type of problem, and then subject to these conditions. We can now, if you now look closer at what we have here, we can now actually rewrite this as a matrix times a vector. Remember again that everything here are just scalars. At the end, this is just an inner product of two vectors, that's a number. The yi and yj are numbers, lambda I and lambda j are numbers. But what we can do now is to do a slight rewrite in a more compact form. And then what we do now is we define two vectors. We define a vector, the transpose one for the lambdas. So I have a lambda 0, lambda 1, up to lambda n minus 1. And then I can also define a vector y of t. And this is given by the output, actually, which take values -1 and +1. So what I can do next then is actually to rewrite. If you look at this term here, the first one, I can rewrite this one as a vector multiplied with the unit matrix. So this first term is something which I now rewrite. So I'm going to rewrite the problem. So I'm going to have a lambda, and then I'm just going to have the unit matrix multiplied with this vector lambda. And that's nothing but the sum which we had previously. And then I'm going to have a minus, and then I have a 1/2, and I have a vector lambda t, and it's easy to convince yourself that this is actually correct. This is just more compact expression. And we have then, in the first element here, we have y0 times y0, and then I have x0 transpose. So remember that the x's are vectors. And then we have a y0, y1, x0 transpose, x1. And this goes all the way up to y0, y of n minus 1, x0t, and xn minus 1. And down here we would have a y of n minus 1, y0, x of n minus 1, x0, and all the way up to yn minus 1, yn minus 1, x transpose n minus 1 multiplied with x n minus 1. And this is a dense matrix. And this is multiplied again with the vector lambda. And this is just a compact way of writing out the matrix here. And the problem in terms of a matrix times a vector. And the thing now is that when we now change things and we change these x's with a transformation, then the matrix here is going to stay, it's only going to change, but the structure is going to be the same, but the values will change. And then we will have the lambdas as vectors on the left and the right. And this is going to be subject again to the problem which we put up, subject to, and I have my y of t times lambda is equal to 0. That is the condition which I put up here. The sum over lambda I times y of I. That's the inner product again. You can always write that kind of product of this quantity here in terms of an inner product. And then we have the final conditions which we also need to plug in. And we have these conditions here, which also need to plug in. And then I'm just going to add plus the KKT conditions. And the KKT conditions are those which we put up here. So let me just frame them in. Now these are the KKT conditions. And this belongs also to the KKT condition. This condition here follows from the optimization of the Lagrangian. But the conditions which are framed in, these are the KKT conditions, which I just restate here, just a line here, so just rewriting the same equations again and again. So if we now, when we solve the problem, we can then find this intercept. We can then find the intercept. Let's put this in quotation mark. And what we have then is by just solving, we find then when we solve this optimization problem, we actually find the W's, and then we can find the intercept, or this W0, by simply putting that one equal to 1. So that means that W0 is given by 1 divided by y of I minus WT of x of I. And with that one, we can then define the support vectors. And these are the vectors which are on the margin. So if we then go back to the Jupyter notebook here, so let's do that and take a quick look at that before we end the day today. So I just need to, here we have it. So the kind of cases which we have been looking at till now are cases like the one you see here. And here we can define very well a hard margin. But let me just scroll down a little bit here and see examples which are not that transparent as these ones. And that's going to introduce something which is called a slack parameter, where we then can allow for problems where the points are within the margin, or even more complicated problems. So this normally leads to a soft classifier, which we're going to define tomorrow and discuss in more detail tomorrow. But I wanted to say something about kernels. So this is a way by which we could transform the data. So let me just run this code here. And if you now look at this figure here, this is an example of where you can transform the original data set, which is to the left. And in this case, we have two classes. So we have the triangles and we have the squares, the blue ones and the green ones. And this is they are plotted as a function of x1 and x2. Now, what I can do now is to make a transformation of my data set where I now just square the points. If I square the points, what you will see then is that the green points, since they are small, they will stay below 4, right? If I square the values. So this is a typical example where I, with a simple transformation, can transform my data by just squaring the points here into something where I can actually find a well-defined separation between the classes. So as I said, you can have cases where the two classes start mixing much more and more. And then by some clever transformations, we can actually again gain two well-defined classes, well separated. And then we can apply the same machinery which we described till now. If this is still not possible, the standard recipe is actually to use something which is called a soft classifier, and that introduces a slack parameter where we allow for some points to be misclassified. And this is what we are going to discuss tomorrow. So now we've just gone through the hard margin. Tomorrow we add this complication with either transforming the data set or to introduce this slack parameter, which allows for some misclassifications. And then by tomorrow, we will have ended the topic of support vector machines, which is actually a very interesting field. But you have to keep in mind that this method is obviously limited by the size of the matrices which you can deal with. So it's a typical linear algebra problem transformed into an optimization problem. But it's a very, if your matrices, if the problem is not too big, this is a very good method, in particular for classifications. Okay, so this ends the day today, and tomorrow we're going to try to wrap it up. And then we are going to dive into the last topic this semester, which is an introduction to unsupervised learning. And then we are going to meet something which is called principal component analysis, which allows us to bring back the covariance matrix. And then we're going to use that one to see if we can reduce the dimensionality of the problem. And the final topic we will cover next week is the topic of k-means clustering. And these are the only two unsupervised methods which we will cover in this semester. So the focus of this course is actually supervised learning, where all the data are labeled. Okay, folks, questions? Feel free to ask questions, or if you have things you want to discuss about project number 2, things which are unclear, or yeah, I'm just here. Hey guys, see you tomorrow. Take care. So for those of you online, I'm going to stop the recording.